Sie noch was einstellen, oder? Kommt noch nichts. Ich bin bereit, ja.
So good morning, welcome back to the fourth day of our training school, and I'm happy that most of the standard audience has come back and finally that we had the dinner last night. And now we will have the fourth and last lecture by Erik Panzer. And if you still have some questions on any aspects of this series of talks, please ask them during the lecture, after the lecture, or the coffee break, because I understand that Erik has to leave around lunchtime.
Thank you very much. Indeed, so if you have any questions, approach me when I'm eating croissants, because I probably have to leave right after Lance's lecture. So today I want to do, are there any questions to what we've discussed so far? Otherwise, today I want to start with just very briefly summing up some of the aspects that we talked about before. And then I want to go into some algorithmic aspects of computing Feynman integrals from the parametric representation. And hopefully there's some time maybe to look at some examples at the end. So what have we done? So recall, this is very wet. So we've derived parametric representations, and we discussed at length why they are well defined and where they converge and what properties they have. And the upshot you can summarize as follows. So we had a Feynman integral. It was a meromorphic function. Can you read this, or is it too small?
I think it's a bit small.
Yeah. It's a meromorphic function of the indices and the dimension. And we talked that you can read off the poles from the Newton polytope and so on and so forth. Of course, if it's a meromorphic function, you will have some poles, and then you can ask about the Laurent expansion in a pole. And the point that we made in the lectures is that you can use integration by parts to always derive a convergent integral representation. So one way to write this down is that so every coefficient of the expansion of the Laurent series, the expansion around. Of course, you can expand around any point that you like. And something special happens when you expand around special points. So let's suppose we expand around an integer point. So suppose we're expanding around values d0 and indices 0, which such that the indices are integers, and the dimension around which we expand is an even integer. Yeah. So this happens quite often. So in most applications, actually, you will have the ends to be 1 or 2 or close to an integer with a little epsilon maybe if you have some one-scale subgraph, or if you're in position space and not in momentum space in Limerick. So that's usually the easier thing to do. And the dimension, well, if you're in 4 minus epsilon dimensions, then, well, 4 is an even number. That's good. 2 is also good. 3 is bad. And I'll try to explain why this makes a big difference for the analytic aspects of the function of the kinematics and the integration technology. Of course, it doesn't. I mean, even if you're in an odd dimension, you still have IBP and everything is the same. But just for the integration purposes, this does make a difference. So suppose we want to expand our Feynman integral around such a point. So then every coefficient in the expansion of the Feynman integral around such a point admits a convergent, i.e. well-defined, integral representation so we can write this coefficient as follows. So there's, remember, on our formulas, there's some gamma functions which are trivial to expand. This is well known. So I really only want to talk about the integral. So we have some integral over the positive reals in our n variables our Schwinger parameters. And then what are we integrating? Well, we have some function f, our integrand. And this is a convergent integral. And what does this integrand look like? Well, this f, well, it's a polynomial in the Schwinger parameters. Remember, we also have the u and f polynomial. So it will be some numerator polynomial divided by some power of u and f. So you can write it like that. So it's a polynomial in these things. And this is if you would just evaluate at an integer point. But now if you expand around a point, then we get logarithms. So we also get the logarithms of the variables. And we also have the logarithm of u, the logarithm of f. I mean, you could do the same thing with the Lie-Pomeranski combination u plus f, but I decided to use the other representation with u and f individually. So we can derive from the formulas we had expressions of this type, which we know when we integrate, we get the coefficient in the expansion. And moreover, this is not just, the coefficients of this polynomial are not just arbitrary complex numbers. I mean, the coefficients come just from the derivation of the representation. So actually, these coefficients here will actually be will be rational functions in the kinematics. Yeah, so in SIJs and masses, right? So this is, so you can be more precise about what the coefficients of these polynomials are. Sorry? No, the integrand is still a rational function. In the u and f polynomial, you only have polynomials in masses and kinematics. Once you integrate, you might have to take roots or whatever. So the integrand is of this form, and we can compute it. So just to be very clear here, let me do an example, the one we did several times. So let's look at the triangle integral, yes, in d equal 4 minus 2 epsilon dimensions. And let's do the case where we use the propagator exponents just to be equal to 1. Yeah. So you just take the scalar integral with usual 1 exponents, and you want to look at the epsilon expansion. And let's say we want to expand around 4, so we just want the small epsilon Laurent series of this. Well, remember we had the superficial degree of convergence, which is the sum of the ends. So it is 1 plus 1 plus 1. And then we have one loop times d over 2. So if you work out what this is 2 minus epsilon. So the whole thing is 1 plus epsilon. So the parametric representation in this case, so that this integral of the triangle is, we have this gamma function prefactor 1 plus epsilon. All the other gamma functions are just 1 because of this special choice. And then what do we have to integrate? I think I forgot the delta function there, but it doesn't matter too much. Sorry, so we have a threefold integral now I put the delta function. And if you work out what the exponents are from the formulae, this is 1 minus 2 epsilon. And the f polynomial comes with 1 plus epsilon. And in this case, we can just set epsilon to 0, right? So this is a convergent case. So in 4 dimensions, this thing is convergent. And this means we can just expand under the integral sign. Yeah, so what do we do? Well, we can just, so this integrand is the same as the delta divided by u over f. And then we have u squared over f to the epsilon. And now we can just expand this term. So this is delta uf. Then you have a sum k from 0 to infinity, just expanding this ratio. So you have epsilon to the k over k factorial. Then you have the logarithm of u squared over f to the k. And the point is that you can now commute the sum with the integral, and then you can read off the kth coefficient of the expansion of this integral. It's just the integral of 1 over uf times a certain power of this logarithm. And of course, you can use the function equation for the logarithm to expand the logarithm here in the linear combination of log u and log f. Okay, so this is just an explicit, very simple case of this. And we computed last time what the leading term in the series is. It was this dilogarithm computation, where we just integrated 1 over uf. Now, in a general situation, when you have an integral with lots of divergences, this can, of course, be much more complicated. So you have to do some integration by parts to arrive at a finite integral representation where you can expand in the integrand. But we discussed that you can always do this. There's one modification here. So here we only expanded in epsilon, right? But the point I wanted to make is that the whole thing is also analytic in the n. So what would happen if we would also expand in an n? So now, more generally, suppose we set n e equal to 1 plus nu e, where nu is a small number. So we want to expand also the exponents around 1. Well, what happens? Well, the superficial degree of convergence is now 1 plus epsilon plus nu 1 plus nu 2 plus nu 3. And if we work out what the integral representation is, we still have the gamma function, we have the integral, we have the delta, we have the uf, we have the u squared over f to the epsilon. And then the extra contributions from these nu's, remember they also sit in the integration measure. So we also have the product over all of the edges. And then we have, if you work out what it is x e times u over f to the nu. Yeah, so this is just what you get when you expand. And again, if you have some gamma factors which you know how to expand, which don't contribute to the integral, so you can put them here. So really you only have to worry about this term, and again you can expand this in terms of logarithm of u and f, and also the logarithm of x. So this is why I wrote this expression up there. If you take all of these logarithms of the x's, the u, and the f, then every coefficient in this expansion can be written like that. And one case when this can come in handy is, for example, when you look at an integral, even in classical Dirichlet, where you don't deform the exponents, but if you look at an integral like this, everything internally massless, then you know that this bubble integral, and we also talked about this one-loop bubble integral, but just by dimensional analysis, right, you know that this one-loop bubble integral is something like minus p squared to the, what is it? D over 2 minus 2, just by dimensional analysis. And then you have some gamma functions, right? Then you have some epsilon expansion, multiplying it. But as a function of the momentum running through it is just a power. So you could also, so to say, integrate out this bubble and just replace it by a single propagator. So this is this function here, some expansion, which does not depend on the momentum, just on epsilon, times the triangle integral. But now where this edge is raised to the power d over 2 minus 2, which is minus epsilon. Right, so you can reduce this 2-loop integral to a 1-loop integral. The price you have to pay is that now you have to look at this integral with an epsilon-dependent exponent. But then again, you can find a finite version of this, and then you can just mean that you have to throw in a couple more logarithms. Okay. So this is one application of these exponents. So one consequence of this, remark. Such integrals are called periods in mathematics. So this is a term that was coined by Kontsevich and Zaghi. So they were saying, well, in mathematics you study classes of numbers and you try to make them more and more complex, and you start with integers, then you want to solve equations in integers, well, then you need rational numbers. Then you want to solve more complicated equations like polynomials, and at some point you need algebraic numbers. But what comes next? And somehow the idea was, how can you take something that you already understand, like algebraic or rational numbers, or polynomials, you know, where you have Galois theory and things, and make something more complicated out of it that is still described by algebraic data. So they say, well, what is a period? Is a more complicated type of number. It's an integral, which is described in an algebraic way. So a period, so this is a number, so this is a complex number, that can be written as an integral over some domain of some integrand. I'm being very sloppy here. Let me write omega. So the integrand is a rational function. And the integration domain is supposed to be a sigma. Domain of integration. Well, what you want is that the boundary of the domain also has to have a description in terms of rational functions, or it suffices to use polynomials. It's contained in the union of some polynomials. So this may seem a bit abstract, but of course this is exactly what we have, at least to leading order, right? To leading order we had this integral 1 over UF. What was our integration domain where we integrated from 0 to infinity? We integrated over a cube. I mean, there was a delta function, right? But you can use the delta function to set one variable to 1, and then you just have the cube and one variable less, or whatever you do. As long as you choose your delta function, the h to be a polynomial, then the boundary of the integration domain will be described by a polynomial. So here the boundaries are described by x equals 0 and 1 over x equals 0. So these are rational functions. The integrand is a rational function, so that's a period. Now when you throw in a logarithm, you might object because this is obviously not a rational function, but you know that you can rewrite the logarithm as an integral, as Johannes explained. So if you rewrite this now as the integral from 1 to x dt over t, you can rewrite all the logarithms in this expansion in terms of a very high dimensional integral, but in the end you can always reduce it to a rational function. And one important aspect of this story is that once you have a period, there's a lot of technology you can use, and there is something special about this period. So if you just take a random integral of some transcendental function or whatever, it will not share some of the nice properties that period integrals do. So because you have a period, for example, you know that there is a Picard-Fuchs equation solved by this integral. So you know that there is a differential operator, this differential equation in terms of the remaining kinematical variables that is fulfilled by this thing as a function. So it's a differential equation of polynomial coefficients. I mean, you will not be surprised by this because you know that for a Feynman integral as a regulated expression, there is differential equations. But already this is the highly non-trivial fact that the number of master integrals is finite. This is what you're using to show that there is a differential equation for Feynman integrals.
In the most general cases, there some interpretation in terms of the original word, meaning of the word?
Yes. I mean, the idea is when pi is somehow the simplest period, pi is... Yeah, so the next period would be the period that the planet takes to go around the center of the solar system. And so that's an elliptic integral if you want to express it in terms of the ellipse that you're on. So this is... No. I think it's really motivated by these classical examples of elliptic integrals. Yeah, so...
So it's not, the periods are not periods of some function?
No. I don't think you can write down for any period you can write down a function which...
But you can make a function.
Yeah. No.
Naturally.
No, I don't think so. Okay. I'm afraid. So you know that each individual coefficient also has a differential equation which follows from this period property. It's also highly non-trivial. Here you're using that the cohomology of of an algebraic variety is also finite dimensional. So there's the existence of a differential equation with polynomial coefficients is always using a very deep theorem about some finiteness somewhere. But here you have it for the Feynman integral as a whole as an expansion, but also for the individual coefficients. And you know that you see that neither one implies the other, right? I mean, you can have a differential equation for an epsilon expansion, but it might just tell you that each coefficient, the derivative of a coefficient is just expressed in terms of the next coefficient, so it might not close the system somehow. Right? Anyway, enough rambling. So these are some properties, and one property which has gained a lot of attention recently is it means that there are motivic versions of this. There are things called motivic periods. I think Johannes might have mentioned this. Also in his talk, he mentioned motivic multiple zeta values. So there are motivic periods. And this would be an entire lecture course. I cannot really say anything that would be meaningful, unfortunately, here. But it's a very interesting development that is very active at the moment. And here the idea is that you try to use this algebraic data that underlies these coefficients, right? So what do you have here? You have a variety. You have polynomials that describe you a hypersurface, or maybe two hypersurfaces. And this is a geometric object. There is many, many decades of algebraic geometry, centuries that have studied this. And you know a lot about these kind of geometries. You can study differential equations. You can study differential forms, cohomology groups, and different canonical maps between these type of objects. So the idea is to use all of these tools to learn something about these numbers, right? Because if you just think of them as an integral, as the integrated expression, you only have a complex number, or maybe a function of some remaining kinematic variables. But of course, the integral representation themselves is a much richer object, right? You have all of these differential forms, you have cohomology groups, you can try to play different games. And some of the magic is that it turns out that at least conjecturally, the numbers actually have more structures. So if you look at a number which happens to be a period, then somehow the number remembers some of the properties that were inherent in the integral representation for the number. Now, this is a very surprising fact because you can write one number in many, many different ways as an integrals. There's infinitely many integration by parts identities. You can write down pi in a gazillion ways. And the integral representations always look very different. But there are some properties of these integral representations that are shared among all representations. And this leads to motivic periods, motivic Galois theory. So there is a way in which you can say, for example, that the number pi and the number zeta of 3, which are they're just some real numbers. You can write down integrals for both of them, that's fine. But if you think of them motivically, and conjecturally this should be equivalent to just thinking of the numbers, then you can really show that they behave very, very differently. So there's a kind of Galois theory that tells you that this is a one-dimensional representation of the Galois group. This is a two-dimensional representation of the Galois group. You can also think of, instead of zeta 3, maybe a simpler thing is just a logarithm. There's a logarithm of x. If you think of it motivically, again, this is a two-dimensional representation of the Galois group. This is a one-dimensional representation. I mean, I just wanted to say one more sentence maybe. So one way to see this in this example, for example, if you want to write down log of x as an integral, you have a problem, right? Because I'm saying you, well, I have this integral of this nice differential form from 1 to x. But how do you go from 1 to x? It depends, right? If you go around 0 in between, you get a 2 pi I extra. So the problem is that it's if you're only allowed to tell me what is your integrand and from where to where do you integrate, you cannot tell me what log of x is. There's this inherent ambiguity of 2 pi I. And no matter what integral representation of log of x you choose, you can do any change of variables, there will always remain this 2 pi I ambiguity in log of x. Pi is different, because here I can tell you just integrate along a path which does not have a boundary. And then you get 2 pi I. You always get 2 pi I. I just tell you wind bonds around 2 pi I, and you're done. No, you're not allowed to tell this, but you're allowed to tell me that you don't have the endpoint and the starting point of your path of integration are the same. This is a residue. So you should be very surprised that there is something for these real numbers that really distinguishes them. And you can use this for transcendence proof. So this is why transcendence, as Johannes mentioned, becomes very easy in the motivic setup. Because in this motivic setup, you can really show that this is linearly independent of this, and also the zeta values are linearly independent. So there's a research effort now to really try to apply these very general techniques from periods to the very special case of Feynman periods. So look at Feynman integrals, think of them motivically and try to compute their Galois representations for the motivic Galois group. And this is very exciting stuff that I'm not going to talk about any further. Yes?
X was in the two-dimensional representation. I guess 2 pi I is the other.
Yes.
What's the analogous thing for zeta 3?
1. The extra generator is 1. So whenever you want to write, so remember there's zeta 3 is a special value of the trilogarithm, and the trilogarithm is the integral of the dilogarithm, which is the integral of the logarithm. So you can write this as a triple integral from 0 to 1 dt over t, 0 to 1 to t dx over x, integral 0 to x dy over 1 minus y. So this is what Johannes wrote down. It's a rational integrand. But the point is, if you take this geometry, right? So you have certain hyperplanes where stuff happens when y is 1 or y is x. This is a singular hyperplane. So, but if you look at this geometry that you have to work in on this, to think of this integral geometrically, then you can always find another integrand which will integrate to 1. But it's impossible to write down an algebraic integral for zeta 3, which does not also allow you to write down, just by changing the integrand a little bit, 1. Whereas for 2 pi I, right, if you look at the integral dt over t around a closed path, you get 2 pi I. There's nothing you can do. You can take any...
Put t in the numerator, you get 0.
Yeah, but then it's not a differential form. I mean, these stupid things are disallowed. This is already work on cohomology. So you're saying you cannot change the integral and you're not allowed to do to add a total derivative in this way. So this is the only thing you have which is not a total derivative. And this fixes 2 pi I. Here you have two different things which are not a total derivative, and the other one integrates to 1. And you can, no matter what representation for zeta 3 you use, you cannot get rid of the fact that there is another integral which is not a total derivative, which gives you 1. Okay, I mean this turns into something that I didn't want to talk about. Any questions though on this part? I mean, I'm sorry that I cannot go into more detail, but this would have had to be a different, it needs to be a separate set of lectures. I think I want to say a little bit too much, so maybe I skip something. Has anybody looked at the exercise from last time? I wrote down a propagator integral, which I claimed had an infrared divergence. Okay, nobody shouts, so nobody did it. Okay. Okay, let me just spend 5 minutes on this, and then we go on. So one other example of periods is when the superficial degree of convergence is of order epsilon. So what happens if you're expanding around a point where the superficial degree of convergence is 0, right? So this means you're looking at a logarithmically divergent integral. Well, what happens in this case, right? You know we have a gamma as a prefactor times an integral and here we had d over 2 minus the superficial degree of convergence. You get f to the superficial degree of convergence. So if this superficial degree of convergence is close to 0, well, you see actually the f polynomial disappears, and you're just left to leading order with the integral of 1 over u to the d over 2. But you also see that there is a pole from the gamma factor, right? So logarithmically divergent integral always has this pole, and the pole comes with a coefficient, which is just the integral of u. And then you have higher order corrections, of course. And this is just reproducing the fact that you all know very well that if you have logarithmic divergence, then the leading divergence, or if there's no subdivergence, the entire divergence is independent of kinematics. It only has the u polynomial, which doesn't depend on kinematics. Of course, you know this has to be the case, and then the residue is exactly this type of thing. Now, this is called the period. So, I mean, it's obviously just one period in the sense above a particular period, but it has been studied in the literature on motivic Feynman integrals for quite some time, and it's often referred to as the period of a logarithmically divergent graph. We call this P of the graph. Yeah. So it's the kinematics independent thing, which is the residue at vanishing superficial degree of convergence. And now I can make these formulas more precise that I very reluctantly wrote on the board last time. So if you have residue when the superficial degree of convergence of a subgraph vanishes, right? So these can describe you the singular hyperplanes of a Feynman integral. The Feynman integral of a graph, and the residue factorizes, and there was something with the subgraph and with the quotient graph. And for an ultraviolet graph, the subgraph is now a superficial degree of convergence 0, so it's logarithmic, so it doesn't depend on kinematics. So what you should put for the subgraph is this period of the subgraph times the Feynman integral of the quotient graph. This is the UV case. And then we had an infrared case where we had this infrared degree of convergence. And there the roles are just reversed. In this case, it is the quotient graph which becomes logarithmic, and the subgraph is the one which you keep. So this is just what I wanted to do in this example. So if you look at this Mercedes example from last time, so this is a propagator integral. There's nothing on shell. Everything internally is massless. Yeah, so it's not maybe an infrared divergence in the sense that you like to think about them, but it does have a soft infrared subdivergence. And where is this subdivergence? It's when you look at this subgraph here. This is your little subgraph gamma. Because you notice that this subgraph connects all the external legs, so it spans the momenta. So when you quotient by it, you have no external momentum left. So this was this mass momentum spanning condition from last time. There's no internal masses here, so this is an infrared subgraph. And what is the superficial degree of convergence? What is the omega infrared of the subgraph? Well, as I said, it is minus the superficial degree of convergence of the quotient graph. Yeah. And what is the quotient graph here? If you shrink the orange part to one vertex, well, you will see you just get this graph here, just the star. And now this has 6 edges, 3 loops. Yeah, so this omega here, we have 6 edges, and we have 3 loops. So in 2 minus epsilon, so this is d over 2. Right, so the power counting here is minus 3 epsilon. So when epsilon is positive, when you're in less than 4 dimensions, then this is an infrared divergence. Right? So in this limit, you just get, so if these momenta here, if these 3 loop momenta are very soft, right, then this subintegral factorizes off from this momentum, and this momentum here is not disturbed. So we conclude that the residue of this Feynman integral for this graph at minus 3 epsilon going to 0, right? So the residue at this singularity factorizes into the period of this vacuum graph times the Feynman integral of the subgraph. Now this is easy to do here, right? This is just a tree amplitude, so this is just to leading order in epsilon. This thing here is just 1 over minus p squared squared, because we have two propagators with a momentum running through it. And this, well, so here we're saying that this residue can be expressed in terms of the pole of this vacuum integral. So this is something you know from the calculation of the beta functions. So I'm telling you what the answer is. This is actually there's another way how you can start this whole period business. So this turns out to be 6 theta of 3. So from all of this, you conclude that this integral here, it does have a pole. And what does the pole look like? Well, it's 1 over minus 3 epsilon, 1 over minus p squared squared, 6 zeta of 3. And then we have finite terms. Yeah. So I just wanted to show this factorization in an explicit example. Any questions on this?
Maybe a strange question, but if you work like you, for example, for many years on this, you must have some intuition about just looking at some graph, what kind of numbers you get, and then numbers. That's sort of what your talk is about. Like,
yes.
Is there like a hand-waving way to maybe somebody who is not working with this also able to learn that
yes.
looking at this graph, this must be because 3.
So telling you exactly what number comes out is impossible, because the kind of statement you can make is what is the class of numbers that the epsilon expansion will evaluate in. So what you can say is that every coefficient in the epsilon expansion of this graph will be a multiple zeta value or some slightly more fancy polylog or maybe something elliptic. So this is the kind of answer you can be hoping for. Or something worse. And indeed, this is one of the big goals in the game, to try to find ways to characterize classes of graphs which fall into certain categories. And I'm going to explain now how you can try to predict the classes of numbers you get. But this is an algebraic thing which you do by looking at the polynomials. So this is not something you can say combinatorially. There are, though, a couple combinatorial criteria. So there's one that was worked out by Francis Brown, and I have a very slight generalization of this in my thesis, which uses recursive construction. So you look for a graph class which has a nice recursive representation, and then you hope that you can make a statement that every integral in this class is of a certain type, and then you can prove that also if you do one more integration, you stay in this class. So this is the only approach at the moment that we have to make statements about infinite families of graphs, which are not just a case-by-case analysis. And the original example that Francis gave is actually very easy to state, and it does cover the 6 zeta 3 case. So there is, for example, you say, okay, I'm not going to be very precise, but suppose you start with a triangle. Yeah, that's a fun graph. You know this graph inside out. This is very easy to do. And it has 3 external legs. Now I'm allowing you to do 2 things, 2 moves to such graphs. I define a class of graphs with some construction. So it has the triangle in it. So this is in my class that I call WV3. Then for each graph, which is something which has 3 external vertices in this class, you're also allowed to add an edge between any of these 3 vertices. So you can also take the graph and add an extra edge. So this is also in your class. And you're allowed one more move. Again, you have a graph gamma. Then you can also add a new vertex. So you can take what you already had with 2 external vertices. And now one of the legs that you had here now becomes an internal one in a sense. You add an edge and a new vertex. And now this is the new vertex you're operating on. So now you can edges from here to here and from there to there and add another vertices. So the class of graphs you can construct this way is called graphs of vertex width 3. That's just how our Francis called it. So for example, what we had falls into this class, right? Because you can start with a triangle. Then you can add an edge. So you have this down here. And now I add this vertex. I do the second move. This move here. And now you can just add the remaining two edges, right? Then you add one more edge. And then you're there. So this wheel graph with 3 spokes, as it's also called, is in this class. And then the theorem is that every coefficient in the epsilon expansion of a graph in this class is a linear combination of multiple zeta values. And there are slight modifications of this for more complicated kinematics where you can do things. But this is for the periods, right? For the things which don't have kinematics. There is a version of this with kinematics. And of course, then in the end, you're putting 3 external legs at these marked vertices. And then you can make a statement about the kind of polylogarithms you get. So either do I break now or do I break in like 20 minutes? Do you want to break now or want to keep going? Who wants to keep going? Yes. Okay. So I explain I want to talk a little bit about singularities and Landau varieties. Because this is so far, except for the calculation yesterday with the dialogue rhythm, right, everything we did was very general. And also this Landau variety game is something very general. So I want to postpone everything that is specific to the last 20 minutes of today's talk. So what I want to talk about is polynomial reduction and / singularities of integrals. So the question here is the following. We have an integrand. I mean, in particular, of course, you want to apply it to, or I want to apply it to the integrands you get from parametric representations. But just in general, we have an integrand. The input is an integrand and what does it look like? Well, it was some polynomial, right? And the x's and 1 over u and 1 over f. We also had log of x's. We had log of u and log of f. So we have some integrand of this form, but I'm only interested at the moment in the singularities. So I don't want to look at a specific integrand. I want to say, let's take any integrand of this form. Then what this tells us is that we know where its singularities are, or where its potential singularities are. So the integrand has singularities on, and we like to call the set of singularities the Landau variety. So this is motivated because I assume most of you have seen the Landau equations in momentum space. Who has seen the Landau equations in momentum space? Okay, not that many actually. But there is a very old and important story that in the Feynman integral business, it starts out from momentum space to try to characterize where singularities are. And that goes under the name Landau equations. Now, this is the same idea, just applied in parametric representation directly. So where are the singularities of this thing? So we call this the Landau variety L. And it has two parts. So one part is somehow trivial singularities, which are just for all of the variables. We have these points where the variable is 0 or infinity. Sorry. And that's clear, right? If a variable goes off to infinity, we have a polynomial that might blow up. Also, we have the logarithm, so it can also blow up at 0. So definitely we could have singularities here. But there's also a part which is more interesting and problem dependent. Maybe we have some extra polynomials where we could have singularities. And we call the set of these singularities, of these extra singularities, in this case, it's just U and F. Okay. So this might be a confusing notation, but all I said is that we have trivial singularities at the boundary of the integration domain, and we have some extra singularities which are given to us by the non-trivial polynomials in the integrand. And now the question of the game is, can you take just this data and predict what the singularities of the integrated function are? Well, what can you say about this? So if anyone of you has heard about symbols, there is, for example, a huge effort also made in the amplitudes research in order to find out exactly what the singularities of the integrated function are. Because in situations where the function happens to be a polylogarithm, you can actually identify the letters, or at least the letters have to be a subset of the singularities. So understanding these Landau singularities is very useful in practice also when you want to do some kind of bootstrap approach, or if you just want to analyze the physics, like the implications of potential singularities that might come up from an integral. So how could you do this? Well, it's actually very intuitive if you think a little bit about how we did the calculation last time. So last time we started with an integral of this form. We had this triangle with very explicit forms of U and F. So maybe let's just do exactly that. So let's do the example. So for the triangle, our set of singularities in the beginning was U and F. And now I'm using the delta constraint already to put one variable to 1, x3. So this is U. And then you have F, which has this form. Remember, we had this parametrization for the momenta in terms of the z and z bars, which turns out to be convenient. So this is F. So this was the input of our calculation. Now the question is, what are the singularities after we do the first integration? So, and we did this very explicitly by taking the explicit integrand we had, right? So what did we do? Well, let me introduce some notation. Let's write the polynomials in S. As you see, in this case, they happen to be linear in the variable x1. And this is not essential for the algorithm, but it turns out to be convenient if it is the case. So let us write these polynomials. We only have two. But I want to call the coefficient of x1, I want to call it A. And the constant part with respect to x1, I want to call it b. So a1 is just 1. b1 is, so this is a1. This is V1. Similarly for 2. Yes?
You want to either some x there?
No, I just want to have x1. So I have several polynomials. I is 1 to 2 for the u and the f. And in this case, I want to do variable x1. It's bad notation, unfortunately. So what do we do? So we do this, and then I define a new set of polynomials, singularities after integrating x1. So I denoted s lower index x1. And what do I do? Well, I take all the ai's, I take all the bi's, and I take extra terms, which are certain quadratic combinations. I take pairs of different entries, I and j different, and then I take the combination ai bj minus aj bi. And I'm claiming that this is an upper bound on the singularities. Well, if you think of how the integration works, this is pretty clear, right? Because where does ai come from? Well, suppose you have your integrand is supposed to have is allowed to have singularities here, right? So it could happen that you're integrating 1 over x1 a1 x1 plus b1, right? And this is exactly the u polynomial. Yeah? You could have this, and because you're a polynomial, you could have x1 in the numerator. And now, if you're evaluating this at the integration boundaries from 0 to infinity, right? Of course, you get 1 over a1. So whenever a1 gets 0, you might create a singularity of the integral. And same with the bi, right? If you have 1 over a1 x1 plus b1, or ai x1 plus bi, and now you evaluate this at the lower boundary, you get 1 over bi. So again, if bi was 0, this could introduce a singularity. And these terms here, these are called resultants. You can see these, for example, from the partial fraction decomposition. Right? So what did we do in the integration? Well, suppose you have this. This is exactly our integrand in the tree level case, right? We have 1 over u times f. So we have this kind of denominator. And then in order to integrate it, we did the partial fraction decomposition, right? So how did this go? Well, you get this term. And then you have to make sure you cancel the numerator of the constant part. And it's exactly a1 b2 minus a2 b1. So you see, just algorithmically, if you were to integrate this in the way we did last time, then you would create, after the integration of a1, you would have this as a new denominator. So when this combination now becomes 0, in principle, you could create a singularity, right? So it is clear that you should have all of these terms in here. What is surprising is that this is even enough, right? Because we only looked at very simple integrals of rational functions. Now you could also throw in logarithms of these things and so on. But the theorem is that no matter what function you have, which has singularities contained in a set of polynomials, if you do this game, you always get an upper bound on the singularities of the integrated function. So this is a very simple-minded approximation of the singularity set, but it turns out, with a few extra tricks, to be extremely useful in practice. So let's do this in the example. As x1 is, well, what do we get from the coefficients? Well, we have a coefficient 1, and we have a coefficient x2 plus zz bar, right? Then we have constant parts, which are x2 plus 1. And what is the constant part here? If we put x1 to 0, it's just this thing. 1 minus z bar x. And then we have to look at these resultant pairs. But you see, we only have 2 polynomials, so there's only 1 pair to look at. And that's exactly the resultant of u and f. So this is precisely the term that we get from the partial fraction decomposition of the 2. And if you remember last time, this is exactly why we introduced z and z bar, to be able to write this quadratic polynomial in a nice way. So this resultant from last time was exactly x2 plus z times x2 plus z bar. Okay. And indeed, this was all the terms that we had after integration. Right? We had a logarithm after integration, and this x2 plus z bar and x2 plus 1, and these were exactly the arguments of the logarithm, so these are singularities. And this was the denominator, so this was the singularity, so we had exactly these singularities. So that was good. And now we can factorize and remove constants without changing the lambda variety. Remember, what are these supposed to represent? The vanishing of these polynomials are supposed to be the singularities of the integral. Of course, 1 never vanishes. 1 is never 0. Yeah, so this is not actually a singularity. If 1 were 0, it might be a singularity, but 1 isn't 0. So we can forget about the 1. And also here, well, when is this 0? But for this to be 0, well, either x2 has to be 0, or this has to be 0, or this has to be 0. Right, so we can just separate them all individually. So after this reduction, this thing becomes just, forget about the 1, so we have x2 plus z bar. We have x2 plus 1. This x2 individually we can also forget because it's already in this boundary term. It's one of these stupid singularities. We already know that at x2 equals 0, there could be some problem anyway. So we don't have to keep track of it. So we have 1 minus z bar. And then finally we have x2 plus z, x2 plus z bar. Okay. So now we've understood the singularities after the first integration. And the idea is now you can just keep going, right? We have, in the same situation, whatever we integrated, after the first integration, we will have a function which has singularities in this variety. And now we can just play the same game again. So this is called polynomial reduction. You keep track of a set of polynomials, which in this example are all very simple polynomials, but trust me, they can get quite horrific. You trace the polynomials that describe you a boundary on the locus of singularities, and you reduce one variable at a time. So let's do the next step, and then we're done, because there is only one more integration. So after we integrate or reduce in this language x2, what do we get? So now I denote this as x1 comma x2. So we first reduce x1, then we reduce x2. What do we get? Well, we get all the coefficients of x1. But you see, the coefficient of x1 is always 1. And we don't care about 1 because 1 is never 0. So these a's do actually not contribute. Now we look at the b's. So what do we have to do? We have to set x2 to 0. Well, if you set x2 to 0, what do we get? We get z bar. We get a 1, which again we can't forget about. Then we have 1 minus z bar. And then we have also z and z bar. Right? And finally, we have to look at these resultants. So first of all, notice that the resultant is 0 for the resultant, we only have to take functions which depend on x. So we only have to take these 4 things which depend on x, and we have to take all pairs of them and look at their difference. Right? So you work out all the differences, and you see, for example, if you take the resultant of x2 plus 1 and x2 plus z, you just get z minus 1 again, which we already had. But there is a new thing that happens. If you take the resultant of these two, you get something that's z minus z bar. And that's one other thing you get new, which is the resultant of the first two, which is 1 minus z bar. Yeah. And now again we can simplify this a little bit. because this is a product, right? And we already have z and z bar individually here, so we don't need to keep track of these. So we have z bar, 1 minus z, 1 minus z bar, z minus z bar. And finally, we have this thing. And now the claim is that this is an upper bound for the singularities of the triangle integral, or stronger for every coefficient of the epsilon expansion of the triangle integral. Now if you remember what we had at leading order and epsilon, what did we get? We had, anybody remembers? We had something like 2 over z minus z bar, and then we had some dilogarithm, and we had its imaginary part. And then I never know, there was a plus or a minus log of absolute value of z times log of 1 minus z over 1 minus z bar. I think it was something like that. So in particular, what do we see? Well, of course we see there's singularities at z equals 0 or z bar equals 0. There is singularities when z is 1 or when z bar is 1. There's even a singularity when z is equal to z bar, right? So at leading order, we see that, first of all, we see that all of the singularities of the function are contained here, right? So we see everything shown. We have z, z bar, we have 1 minus z bar, minus z bar, and z minus z bar. So the algorithm works. We have an upper bound. But we also see that there is a spurious term. Our analysis has showed us that, well, there could also be, in principle, a singularity when z bar equals 1, and we don't see it. Now, this could have several interpretations. It could mean maybe this is just an accident of the particular integral you looked at, right? Because this reduction statement is for all integrals to all orders in epsilon. So maybe at the next order in epsilon, we have a new singularity showing up. And in many examples, it is the case, indeed, that at leading order, you have simpler functions. And in higher orders in epsilon of the integral, you get more complicated functions or numbers. In this case, however, it turns out to be truly spurious. So this is a fake. This is a remnant of the fact that we used a very simple-minded approximation. But we can get rid of this. And one very simple way to get rid of this is just to look at the other order. So what we have shown here is that, well, we integrated with respect to x2 any function which had singularities in this set. And indeed, if you do this, you can create the singularity. There are examples. But the point is that we're not integrating any old function in x2. We're only integrating function in x2 which came from integrating in x1 this very special Feynman integral. So you can also play the same game in the other order. Let's pretend we first integrate x2 and then you integrate x1. But this is an exercise you can do very easily. And it's not surprising that you get a different result, right? Because you do different transformations you compute different resultants. And if you do this computation, you will find a set of polynomials which also contains these four and another polynomial. So it also has a spurious polynomial, but they're different. But of course, you know it doesn't matter in which order you integrate. So if you're allowed to intersect those sets, and then you can get rid of this one. Yeah, so there's a slightly improved algorithm, which is called the Fubini reduction, which you can apply for this triangle integral, which tells you the upper bound on the singularity is exactly the set, and this is exactly what you need. This is the answer for the Landau variety of this Feynman integral. You can retranslate this into momentum space if you're more familiar with this, right? Remember, z equals 0 means that p squared is 0. Z equal 1, this means that p prime is square into 0. And this is the most interesting physical singularity, and this is the Killeen function. This means that, so the most interesting physical singularity, this is when, so this is p squared plus p prime squared plus q squared minus 2 p squared p prime squared minus 2 p squared q squared minus 2 p prime squared q squared. So this is called the Killeen function, which you might know as the leading singularity of the triangle integral, whatever that means. And you can write it as q squared squared. In our coordinates, this turns out to be just z minus z bar squared. Yeah. So indeed, all of these singularities we got from this algebraic manipulation have a direct physical interpretation in the kinematics. But I I find it in practice easier and more algorithmic to apply this polynomial reduction. I mean, you can also try to compute the Landau equations directly in momentum space, and there's lots of work on this as well and results. Just for computer algebra implementations, it seems to be very easy to use this polynomial approach and play some games with that. And then afterwards, you can always ask yourself, well, what does it mean in kinematics, if you're interested in. But that's that. So this is what I wanted to roughly explain. And I think now is a good time for a break. Yes?
Could you repeat the briefly how you went through, like, I assume the first step in which you had a problem to, the integral was in the form you've written down there, and you did the first integration. The second step, when you understood the singularity after the first integration, how you got the second sets of...
I do the same. This is the rule. You take whatever set you start with, and you look at the coefficients of the variable you integrate. You look at the constant parts of the polynomials with respect to the variable you integrate, and you look at the resultants of the polynomials with respect to the variable you integrate. So here I showed you why you should expect that you should do this in order to get the singularities. I also explained that this is slightly surprising that this is actually sufficient, because you could also look at much more complicated integrands and get this. So this is a big, it's not a big, it's a little lemma or proposition to check that indeed doing this always gives you a bound on the singularities no matter what your integrand was. So you now just apply these rules mechanically and you get the set. And so the point is that this is very easy to implement, right? I mean, you can write a Mathematica that does this in a very short amount of time. And also this intersecting with different orders, I mean, if you have 10 variables, it's 10 factorial orders, so it might take some time, but it's trivial to implement in a way. Yep.
You said that Z and Z bar are convenient variables here. What if you have a larger Feynman graph which is less symmetric? Is it always clear what are convenient variables?
Well, suppose we would have not started with these variables, right? If you wouldn't have started with these variables, what would have happened is that this x2 plus z bar would not have factorized into a linear form. In linear forms, it would have been a quadratic thing. So actually, I've only given you the rules for things where the polynomials are linear. So there's an extended set of these rules that works for arbitrary degrees. So what you do is you always take the constant coefficient, whatever the degree is. You take the leading coefficient, whatever that is, and you take the resultant. So the resultant is something that's defined for any pair of polynomials. It's telling you exactly when does it happen that two of the roots coincide. And you know that you should expect this because you have, suppose your integrand is 1 over, if your integrand is 1 over f times g, and f has a pole somewhere and g has a pole somewhere, maybe it's just about integrable. But if the poles coincide, suddenly you have a double pole, so maybe now your integral blows up. So you know that you should actually take the resultant. And so this resultant just gets replaced by the actual resultant, whatever, and there are formulas for resultants in general cases. And then there's one more term, which is the discriminant. So now you have a quadric. So there's one extra singularity that can happen because you have a quadric. In general, it has two different roots. And now it can happen that maybe the two different roots actually become one root, a double pole. And this is exactly what z minus z bar is, right? Z minus z bar is 0 exactly when this quadric has a double root. And that's also a well-defined classical thing that's called the discriminant. So if you have a polynomial, you can always compute the resultant of the polynomial with its derivative. And this is equivalent to saying when do two roots, which in general are different, suddenly coincide for one polynomial. So there's an extended set of these rules for arbitrary polynomials, for arbitrary degrees. And they always give you a bound. And then in this case, so you could still do the calculation, you would end up with the same answer. It would just look more complicated. Yeah. So instead of z minus z bar, well, you would have exactly this thing here. All right, maybe break.